The goal in this video is to show you just a few key steps in using Laplace transforms where you have one of these piecewise defined functions. I want to help you kind of get started and show how this works. I'm not going to work it all the way to the end. I'm going to work it to the point where you can finish it on your own based on what we've seen in the previous videos. This differential equation models the current, IFT. IFT is the current in an LC series circuit. And that is governed by this differential equation here. If that doesn't mean anything to you, that's fine. Some of you who maybe have taken a few engineering courses involving LC series circuits, maybe you've seen something like this, I don't know. But anyway, this is just a differential equation. Whatever the application is, we approach it the same way. We're going to solve this using Laplace transforms. So the very first step is to take the Laplace transform on both sides. And actually, I guess there's one intermediate step. Before I do that, let's use what we learned about unit step functions and rectangular window functions to rewrite this piecewise function g of t. I could rewrite it using the rectangular window functions. This is 3 sine t times that rectangular window going from 0 to 2 pi plus 0 times my unit step function shifted over 2 pi units. 0 times u of t minus 2 pi. But obviously that's 0 is just going to wipe that out. So really all we have to worry about is the sine function between 0 and 2 pi. In order to use our properties for Laplace transforms, let's rewrite this in terms of the unit step functions. This is 3 sine t times u of t, the unit step function that's not shifted at all, minus the unit step function that's shifted right by 2 pi, u of t minus 2 pi. All right, and I'll go ahead and distribute into the parentheses. So I've got 3 sine of t times u of t minus 3 sine of t times u of t minus 2 pi. So this is our function g of t. Now, let's go back to our differential equation and take the Laplace transform on both sides. So I've got the Laplace transform of I double prime of t plus 4i of t equals the Laplace transform of g of t. So the Laplace transform of all of this. And here we'll have to use some of those properties from the previous video. Laplace transform of g of t. I'll just write g of t instead of copying the whole function down. On the left-hand side, I went ahead and wrote just a reminder from one of our tables that we saw in a previous section. If we say that the Laplace transform of I equals capital J, you could use any function name you like, just as long as you're switching from a function of t to a function of s. All right, so we've got the Laplace transform of our current function I of t equals some function of s. We'll call it j of s. And then the Laplace transform of I double prime by that table 7.2. It's going to be s squared times the Laplace transform of I minus s times I of 0 minus I prime of 0. But I of 0 is 1 and I prime of 0 is 3 because those were our initial conditions that we were given. So then we've got s squared times j of s minus 3 is what this Laplace transform of I double prime looks like. So then using that over here, Laplace transform of I double prime, I have s squared times j of s minus s minus 3 plus 4 times the Laplace transform of I, which again we're calling capital J, so plus 4 times j of s. And then the right-hand side of this, again, I'm not going to go into the details, but going back to your properties of Laplace transforms, the Laplace transform, or the previous video that tells you how to handle it when it's the function is being multiplied by a unit step function. This first one, its Laplace transform is just going to be the same thing as the Laplace transform of 3 times sine of t. So that would be 3 over s squared plus 1. And then we're going to subtract off 3 sine t times u of t minus 2 pi, the Laplace transform of that. Using, again, our property from the previous video on how to handle it when it's multiplied by a unit step function, we're going to get e to the negative 2 pi s times the Laplace transform of 3 times sine of t plus 2 pi. Now, one little tip that I have for you here is if you're doing the Laplace transform with trig functions and it's being shifted, a lot of times some kind of trig identity or trig property will come in useful for you. In this case, we know that the period of sine is 2 pi. So if I shift my sine function left or right by 2 pi, then I get back my sine function. So this function right here is just your sine function shifted left 2 pi units, but that just gives you back the sine function. So this is the same thing as sine of t. All right, so keep an eye out for ways that you can take advantage of what you know about your trig functions to simplify these things. Sine of t plus 2 pi doesn't necessarily show up in your table of integrals, but sine of t does. All right, so what we have now is s squared times j of s minus s minus 3 plus 4 times j of s. Then we've got 3 over s squared plus 1 minus e to the negative 2 pi s. And then the Laplace transform of sine of t is 1 over s squared plus 1, and we've got that times 3, so we've got 3 over s squared plus 1. All right, so now just like you've done in a previous section, now we want to solve for j of s. So solving for j of s, if I move the minus s minus 3 over to the other side, and then factor out my j of s and divide. After just a little bit of algebra, here's what you end up with. J of s equals 3 over s squared plus 1 times s squared plus 4. You can do the algebra here and double check and make sure this works out the way I'm saying. Minus 3 e to the negative 2 pi s times 1 over s squared plus 1 times s squared plus 4 plus s over s squared plus 4 plus 3 over s squared plus 4. Now, to get your final answer, you just have to do the inverse Laplace transform. And I'm not going to do this here because we've already covered inverse Laplace transforms, but if I do the inverse Laplace transform on both sides, the inverse Laplace transform of j of s takes you back to your function I of t. So I of t, your final answer, is equal to the inverse Laplace transform of all of this over here. Now, it looks like there's a lot going on, but just to highlight a few things for you, if you want to finish this on your own, you're welcome to, and then if you get stuck, feel free to check with me and I can help you out. But a few of these pieces, like this one and this one, you can read basically straight from your table of Laplace transforms and get those inverse Laplace transforms fairly quickly. This one over here will take a little bit of work because you'll need to do partial fractions. So you'd have to break this up. You'd have 3 over s squared plus 1 times s squared plus 4 equals, when I break this up, I would have an s squared plus 1 in one of my fractions and s squared plus 4 in my other. And the thing to remember here is if you have quadratic terms on bottom, you have to have linear terms on the top, not just constants like a and b. It'd have to be some linear term like as plus b, and then cs plus d. So solve the partial fractions, figure out a, b, c, and d. But once you do that, then both of these, once you know those numbers, both of these will be inverse Laplace transforms that you can handle. And notice this one in the middle is the exact same as this one that we're doing here on the left. The only difference is that it's multiplied by this exponential function. So what that means is if you know the inverse Laplace transform of this one, then you can use the property from the previous video to figure out the Laplace transform of this one, because that's where I told you how to handle an exponential function times something that you can do the inverse Laplace transform for. And this one in the middle, again, if you use that technique that I talked about in the previous video, this one is going to involve a unit step function when you find that answer, okay? So 3 of the 4 inverse Laplace transforms are straightforward, similar to what you've done in previous sections. This one would be new, but it uses the technique that I showed you in just that last video, all right? So I'm not going to go into all the details there any more than I've already said because that would make this video too long. But if you want to try that on your own, and if you happen to get stuck, feel free to check with me and I can help you out.